Okay, all right. So I have started recording. Yes. So we are going to talk about clustering as you have already understood. So let's just, but it may be just a slightly different point of view and so on. So clustering essentially, the idea is that we have a set X of points in some space, and maybe it's a high dimensional space. I mean, in most often that is the case we are interested in. And what will clustering do? Clustering will do grouping of points according to some distance measure. What is a distance measure? So the grouping of points in this case can look like this. Well, if the data is so nicely separated, then it may look like this. And then we can intuitively say that, well, these set of points are like one group, these set of points are another group, these set of points are another group, and so on, which means they fall into one category, these fall into one category, and all that, right? So this is an unsupervised uh, technique in machine learning. Unsupervised, there is no label or any true answer, question answer kind of things given. So this is unsupervised, but you still want to make sense out of it, you want to get some insights out of it. So typically applications, what people do, they cluster data points, and then from, so and they get different groups of points, so different groups of uh, mm, whatever the data is, can be like words. You may want to cluster words. In text, you may want to cluster images, you may want to cluster other semi structured data, or for whatever it is, right? So you may want to cluster customers. So these are, then we will say these are similar customers, these are similar to each other and all that, or products and things like that. And then obviously just grouping will not help you, right? Because you want to then make sense out of it and take actions based on those. So then people try to give some category name or tag or something like that. Okay, so there are many works on automatically giving tag names or category names and things like that. Once people have done some kind of clustering. Okay, so those are the applications. Now, when we talk about clustering, the first thing that is essential to understand is a distance measure. A distance measure is a function from any pair of points in X to non-negative real numbers. That means real numbers, all numbers and zero, such that the distance between the any point to itself is zero, and the distance between 2 points is always greater than equal to zero, and it satisfies the triangle inequality, that if you go from X to Y directly, the distance will be smaller than or equal to if you go from X to Z and then Z to Y. Okay, so um, via some other point. Okay, one property I have missed writing here, that is the so this is actually not the symmetric thing. The symmetric property I have actually missed writing here. So that is distance from X to Y is actually same as distance from Y to X. So it doesn't matter whether you go from X to Y or Y to X, the distance will remain the same. All right. So now, as you must have heard already, there are two kinds of clustering approaches at a high level. One is hierarchical or agglomerative. Another is point assignment. The k-means kind of algorithms fall into the point assignment category, and hierarchical, well, there's a lot of variants of hierarchical clusterings, and basically we'll spend the class today discussing those. Um, yeah. So let's start with hierarchical clustering. The main approach is that initially each individual point is a cluster. Okay, so that is the bottommost level of the hierarchy. We haven't seen the hierarchy yet, so we'll see. So suppose these are your points. Okay, so these are your points. Intuitively, you can figure out that C and F are one cluster, D and G are another cluster, A and D are another cluster. and B is kind of confused. So let's see how it goes. So yeah, okay. So essentially, initially, every point is a cluster. Each cluster is marked in this YOLO circle, and that is the bottommost level of the hierarchy. Means if you want to separate them out the most, then you can make 7 clusters out of the data, right? So you can actually make 7 clusters out of the data. It's like the leaf of the tree. And then what you do, you keep combining clusters based on their closeness. Now this closeness should be related to the distance we talked about. But what do we mean by closeness of 2 clusters? So we know the closeness of 2 points, right? It's some distance measure, and usually we think about Euclidean distance, right? Because we usually think that the points are like vectors in some dimensional space. So we know the Euclidean distance is defined, and usually that's what we think about. The picture here also, we are intuitively thinking about Euclidean distance in 2 dimension in this picture. But how do we combine clusters based on their closeness? Okay, those are the details we'll see in a while. But as of now, let's just go with our visual hunch or intuitive visual feeling. Looks like that C and F are very close, right? So C and F are the closest pair of clusters, right? So the next one, so then we combine them, okay? So I combine them into one cluster. Then next D and G, these clusters are very close to each other. I again combine them. And next, as you can, maybe A and D will be the most close to each other. So again, I combine them. Okay. So now what do? I can combine this cluster and this cluster, right? So this cluster CF and B, they look close to each other. You can argue, doesn't this pair, like this cluster and this cluster, also look close to each other? Well, now it depends on how you define closeness uh, between clusters. Okay, so in this particular case, what we are thinking is the distance between the middle point of this cluster and the middle point of this cluster. Okay, so we'll go into more details about this later, but let's say we combine this, and then we also combine this, and finally we have 2 clusters. We can actually combine them also. So this is our hierarchical clustering, and that means something that we did not do was we did not stop. So we could have stopped at any point which would have made sense, maybe here or here. Okay, we could say, yeah, fine, we are done. Now, this is a good point to stop. You can leave B separate, or this is a good point to stop, or maybe this is a good point to stop. Well, then you never know what is a good point to stop, right? So you have to actually mathematically define some criteria. So obviously one option is, okay, you don't stop, you produce the whole tree, and then while using them, you figure out what to use. So what is the tree then? The hierarchy is initially, now you go backwards, okay? You go backwards, and now you have this whole set as your root of the tree. Okay, then your first two will be this slightly lighter orange cluster, so BCF and AEDG, say these two, and then BCF gets separated into B and CF, AE and this one gets AE and DG, and then B is already a single point, and then you can further divide them into this cluster. So this is the hierarchy, right? This is the hierarchy. Now you can stop at any level where you decide, okay, this is what I want to take. All right. Okay, now let's get into the details. So what are the, so we looked at the picture completely intuitively, and what are the details into it? There are 3 main points. First, how are the clusters represented? So how do we define we said, okay, 2 clusters are close to each other, then that means a cluster is not one point, right? So cluster is a collection of points. We need to represent the cluster by some captain, right? Or some representative. Okay, so who or which point is the representative of each cluster? And then At this point, let's assume the space is Euclidean, so it will make our life slightly easier. So if the space is Euclidean, then the simplest thing to do is each cluster is represented by the centroid of the points in the cluster. And in the previous picture, that's what I was referring to. Let me just quickly go back. Okay, so what we were thinking is, okay, these two form this cluster, and this is the centroid of this cluster CF, right? And then this is the centroid of DG. Somewhere here is the centroid of AE, but the centroid of AE and centroid of DG are not so close to each other, whereas this and B, single point is the centroid of itself, maybe looks closer. I mean, if by eye estimation, and then obviously in the next level, this whole cluster, the centroid is somewhere here, and this next level, the whole cluster, the centroid is somewhere here, and things like that. Okay, maybe here. Okay, so the obviously I'm not going into the definition of centroid. It's just the sum, the average. Okay, just the sum of the coordinates element. I mean, coordinate wise, the sum divided by the number of points. Okay, so that's the centroid. You all know that. Now, so that's the simplest way to think about representing a cluster. But then there are options about how to choose which cluster to merge, right? Which two clusters to merge. So at any point of time, what we did was we merged two clusters into one cluster. So which two clusters should we merge at any point of time? Well, in the example, what we did was we took the distance between two clusters is distance between the centroid. So if we then compute the pairwise distances between any, uh, I mean, between all the clusters, and we merge the two closest clusters. All right, then when to stop? Okay, when to stop? Well, in the previous example, we did not stop at all, right? So we just went on doing because we kind of did not figure out what would be an optimal uh, time to stop. And that is why sometimes we should have some idea beforehand that, look, from this data, I want 5 groupings. So maybe you already have some idea that you have, 5 different kinds of products. Okay, you have 5 different kinds of products represented in some attributes and things like that. However, given a product, you don't have the data of what category it is. So you simply have a lot of products, and you know that there are 5 different kinds of products, but you simply don't have the exact assignment, product and category assignment. So then one thing you can try is, okay, cluster and cluster into 5 clusters, and then figure out, hopefully if you are lucky, if the data is good, if your attributes are representing the distances properly, then you will actually get 5 different clusters where each cluster will mostly represent one category, and then you can actually look at every cluster and say, okay, look, this is this category, right? So that's one possibility when the number of clusters reaches some number, but that is the simplest way of doing it. And often you may not actually know that how many clusters you want. uh, this problem will come back again and again and again. In dimension reduction, we said, okay, we go to low rank and low rank k. How do you choose the k? You never actually know exactly what should be your right k. So similarly, how many clusters should be there? Well, when you are just given a data, you never actually know beforehand, right? So well, it's just a hypothetical case, or theoretically you may know beforehand, but you actually in practice you may not know most of the time. Then the other approach is when, so hierarchical clustering means you start from every point is a different cluster, and then slowly you keep merging. At some point of time, merging further would make a cluster inadequate or make a cluster not so good. Okay, so merging further will not be a good idea based on some calculation. Some obviously some mathematical calculation has to be there. It cannot be just eye estimation like we did in the previous slide. So we'll look at different options of this. So before going into that, let's just quickly look at the efficiency issues of hierarchical clustering. So let the number of data points be n. Okay, so let the number of data points be n, and then initially what do we do? Initially, every point is a different cluster. We have to compute pairwise distances between the centroids, or the points rather. Initially, every point is a centroid of that own cluster. So initially, you have to compute order n square. That means n choose 2 pairwise distances, right? And then at every step, you reduce the number of clusters by 1. You combine 2 clusters into 1. So at the ith step, you compute order n minus I square distances. But if you sum this up, it will actually be, you do this n times, right? I mean, assuming that you actually run through the whole hierarchical process, if you do this n times, this is actually overall order n cube, right? So you n times, you do order n square pairwise distance calculation. So this is order of n cube, and it's very inefficient. Obviously, one small detail we are omitting here that will not change the complexity is once after you compute the pairwise distances, you have to figure out the minimum distance. I mean, you can just naively sort n square distances, and that will be n square log n. Or you could do something like a priority queue and things like that, right? So yeah, so that's what we will actually do now. What we'll do, we'll use a priority queue. So a better approach, we can reduce the complexity slightly. And how? So initially, of course, we have to compute order n square pairwise distances. And then we form a priority queue with the pairwise distances. Because there are n square, order n square distances forming the priority queue in a heap maybe. Okay, you have all done that. We'll take order n square time. Now, when we merge 2 clusters, what's happening? Those clusters had their individual distances with all other clusters in our priority queue, right? So let's say cluster C and D are being merged. C had order n distances with all other existing clusters, and D also had order n distances with all other existing clusters. And those distances have to be deleted from our priority queue because these clusters do not exist anymore individually. So there will be at most 2n deletions, right? So there will be at most 2n deletions, and each deletion is order log n from the priority queue. So there will be deleting obsolete distances, the distances which are no more valid. Okay, will take order n log n time. And now the new cluster has been formed. From C and D, we have formed something called a CD, right? So that new cluster now has distance with every other cluster, and maybe there are order n of them at most. So we have to insert n times, n new distances. So that will be order n log n into the priority. So essentially update this update portion, delete invalid or obsolete distances and add the new distances or insert the new distances. This whole thing, each step is order n log n, and we do this n times. So this can go on for at most order n times. So overall complexity is order n square log n. So that is the dominating complexity. All right, everybody clear on this? These 2 points could be a bit tricky to understand. If you haven't understood, please tell me, I'll repeat. But otherwise, maybe this is fine.
Sir, what are obsolete distances? Can you please explain?
Yeah, so by obsolete, I mean, okay, let me actually go back to that picture. Okay, maybe I should have had that picture copied into this slide also. That would have helped, but let's just go back to that picture. Yeah, let's say we are here. Okay, at some point we are here, right? Okay, now there are 4 clusters at this point of time. So that means in my priority queue, I have the distance between B and CF, I have distance between B and DG, I have distance between B and AE, I also have distance between CF and B. Okay, that is the same, CF and DG, CF and AE, right? All of them are in the priority queue, right? So there are 4 clusters. I have 4 choose 2 distances stored in my priority queue. Now these numbers are small, but think about order n square. So there are order n clusters Okay, and there are order n square pairwise distances stored in my priority queue. Now my next step is I combine these two clusters. So now this cluster is a new cluster and the distances are getting disturbed. So which distances are getting disturbed? The distance between these two clusters are not disturbed because they are not changing. However, previously I had this distance CF and DG, that is not existing anymore. There is no more a distance between CF and DG, this distance, right? That's not there anymore. Rather, I have a new distance, this somewhere here, the centroid to DG. So I have to delete CF to DG, CF to AE, and CF to B, right? So these I have to delete. Also, I have to delete B to DG and B to AE and B to CF. So that means for every for these two clusters, for this cluster CF, I have to delete order n distances from the queue. For this cluster also, I have to delete order n distances from the queue. So that is your obsolete. Those are your obsolete distances. That means in the next step, those distances are not there anymore. They don't make sense anymore. However, what makes sense now is there is a new centroid of this cluster, maybe somewhere here. Okay. And this new centroid now has distance to this cluster and this cluster. So these two you have to insert. Clear?
Yes.
Okay. All right. So yeah. Okay. So basically this means we do at most 2n deletions, order n log n, and we also insert at most n uh, new distances. So this is also order n log n. All right. So order n cube is very bad. That means unless the data is very small, you cannot do. Order n squared log n is also not so good, right? I mean, given a large data on a high dimension, this is not so good. Uh, but then that is why point assignment kind of k-means kind of things are used more in practice. However, hierarchical clustering in some cases can actually, I mean, if the data is not so big, but you want to make a proper sense out of it, it can still give you very interesting, interesting visualization. And there are lots of different approaches, lots of flexibility also um, with respect to how you do certain things. So now let's get into more details or more alternative options about combining clusters and as well as stopping, when to stop. So let's go through them. So there are again within these alternative approaches, the first thing we mentioned was, okay, the clusters are defined by their centroid or represented by their centroids, and two clusters, the distance between two clusters is the distance between their centroids. So the captains, right? Centroids are the captains. If the two captains are far apart, then you know the clusters are far apart. Now there are two primary distinctions again based on how you combine. Now, one approach or one higher level approach is at any step, look at how the clusters are panning out right now and combine clusters by calculating some function based on the current scenario. And that is what we have been doing so far. Currently, these are the centroids. These are the distances between the centroids. So this distance is the smallest. Combine these two clusters. Okay, so compute the something from the current scenario, then do some combination. Okay, so that is one approach. And that one option for that we have already seen. Another is the minimum of the distances between any 2 points. So instead of the captains or instead of the representatives or the centroids of the clusters, what we do here is the minimum of the distances between any 2 points, one from each cluster. That means distance between the cluster C and D would be the minimum of distance x and y, where x is from C, y is from D. What will this do? If the boundaries of the two clusters are close enough, then they will get combined earlier. Okay. So now let me quickly go back to, okay, I'll share again just a moment. Let me go back to that picture. Yeah. So here, uh, at some point, what we did was we combined this cluster CF with B, and we did not combine at that point AE with DG because we thought this centroid and this centroid are far apart. However, you see that A is quite close to D or G, whereas B is not so close to F or C or F, right? So in this approach, we would have combined this earlier than this. All right. So this is one possibility. The other possibility is the average of the distances between any 2 points, one from each cluster. Okay, so this is not really how you write mean, but instead of sum and then divide by 1 by order n square and all those things, I simply write mean of distances xy, where x is from C, y is from D. Now what does this do? Again, this is more intuitively, this is closer to the centroid thing. But essentially, if two clusters have the average distance between two clusters is like you taking into account all pairs of distances from here to there, and then if two clusters, I mean, and then you compute pairwise average distance between two clusters, and then you combine the one which is the minimum distance. Okay, so this was these two were two alternatives for computing some function based on the current situation. Now we're going to see some alternatives based on uh, computing some function uh, based on the future situation. What is the future situation? At any point of time, you're going to combine two clusters and you're going to make a new cluster, resulting cluster. What will happen after that? Okay, so the aiming to optimize a function that is computed after merging, after the merging that is to be performed. So this means it's like thinking one step ahead. What will happen if I merge these two, if I merge these two, if I merge these two, and so on. And I think ahead or I compute ahead, and then I take a decision based on that. So for this, there are two definitions. One is radius of a cluster. Well, it's just like your standard concept of a circle. So maximum distance from the centroid to any point in the cluster. Obviously, here the clusters are not like circles. It's not that there is a center and all the other points are on the circle, but radius means from the centroid, what is the largest distance to any point? If you draw a sphere or a hypersphere from the centroid of that radius, the minimum radius that you need to draw to cover all points of the cluster. Okay, so that is the radius of a cluster. And simply also similarly, diameter of a cluster is maximum distance between any two pairs of points. So how far apart can two points be in the cluster? So similarly, it is also similar to our circle intuition, but here also, what is the largest sphere you need to draw, or largest diameter you need to draw, so that you enclose all points of the cluster. Now, alternatively, radius and diameter can be used. They are similar concepts, but let's see how they are used. So the third alternative, of course, belongs to this kind of approach, is for each pair of clusters, check the radius of the resulting cluster if that cluster is if those two are merged. So if I merge these two clusters, what will be the radius of the new cluster? And merge the pair of clusters which will produce the smallest resulting radius. Now, interesting point, the resulting cluster, okay, so if the resulting cluster has a small radius, it makes more sense to make that cluster, right? And just note that, I mean, it will actually come when we talk about stopping, and note that this radius keeps increasing all the time. Initially, all radiuses are zero because you have one single point. Then you are adding, you are merging 2 points which will make the smallest radius cluster, right? Then you are merging two clusters which will make again the smallest radius cluster. So your radius of largest of the existing clusters is actually just increasing monotonically. So this means this will also help us in deciding the stopping criteria. Alternative 4 is just similar to this, but except that you, instead of radius, you think about the diameter of the resulting cluster. Okay. Any question at this point? Okay. All right. So now let's finish. No, not finish. We were almost finishing, but let's look into what are the alternative approaches for stopping. So obviously, one approach we discussed that the lucky approach. If you know, okay, you want to have 6 clusters, you want to have 10 clusters, you stop as soon as you have those many clusters. But in the other cases, when you actually want to figure out what would be a reasonable size or what would be a reasonable number of clusters based on the data, then these approaches are interesting. Remember that for k-means kind of algorithms, which you have already seen, you actually have to decide a k beforehand, right? But yeah, so here you can actually do more sophisticated things, except that things are not so efficient. So each cluster should represent a group of points close enough to each other, right? So that's one idea. Okay, what is a cluster? That means these things are similar. That means they are group of points close enough to each other, which means the cluster being very big will not make sense. So this means you stop when the radius or diameter of the newly formed resulting cluster exceeds some threshold. So we already mentioned that all previously formed clusters have lower radius, right? So this gives a well-defined condition that your radius of the largest cluster at this point keeps increasing slowly, slowly, slowly. At some point of time, you say, okay, I cannot have a cluster bigger than this radius because then it will not make sense for that to be called a single cluster. Then I stop. Okay, so this is one possibility. You can do this using radius, you can do this using diameter, either way. The other possibility is by density. So similar idea, the concept is similar that each cluster should also be dense, not only small but also dense. Means dense means points are close to each other. But how do you compute density? Normally, you compute density by number of points per unit volume, right? So if you are number of points per unit volume in a 3 dimension, we think about volume. Higher dimension also we can think about volume. Same formula extended. Now, how to compute volume of a cluster? Obviously, here the shapes are not cuboids or hyperspheres, right? I mean, if we are given as cube, we know how to compute a volume. If we are given a sphere or a circle, we know how to compute the area or volume. Sorry, volume and area respectively. But these are not really these shapes of clusters are not really spheres and things like that. So what we will do is we will actually estimate. We'll estimate similar to the case if they were spheres. So it is just that means number of points by some power of radius. If it was a sphere, then it is, if it's a 3 dimensional case, then it is some power of radius means r cube, right? Some constant times r cube. R is the radius. And that's what we do. Number of points by some power of radius. And power, what power of radius? Ideally, the power of radius should be the number of dimensions. If it is a 2 dimensional case, it is pi r square, right? So some r square. The pi is not important because you are only taking relative density, right? So the constant factors are not important. If it's 3 dimensional, it should be r cube. If it is whatever number of dimensions, it should be the number of dimensions. However, uh, in some cases, people just take that power to be 1 or 2. You all know that the one case is essentially the corresponds to the Manhattan distance kind of a thing, and 2 cases L2 norm, and so on. By the way, just one point: have you studied the different kinds of distance measures? L1, L2, L infinity. So L1 is Manhattan, and then like Jacquard we have covered, edit distance we have covered, uh, Hamming distance also we have covered in different contexts. But are you familiar with the L1, L2, and this L norms essentially?
It was covered today.
Oh, great, fine. So so then yeah, so that's fine. So then this is what we have. So the alternative approach is for stopping. That means you stop once the density of uh, the cluster becomes lower than a threshold. Okay, so initially the densities are high because you are combining points close to each other, and then at some point of time you are actually expanding too much, and you stop when the density is lower than a threshold. All right, so the last thing we'll cover is the non-Euclidean spaces. So far we have been thinking about Euclidean spaces, and that helps because the idea of centroid is very well defined. We simply sum the vectors and sum the points and take the average. However, in case your data points are not Euclideans, not in Euclidean space, maybe words, okay, numbers, not numbers, words, or other kinds of attributes and things like that. Uh, then distances can also be defined. We have already done that for the Jacquard distance, edit distance, Hamming distance, and so on. We have seen these. However, there are other challenges. The challenge is how do we define the centroid of a cluster, right? So how do we define the centroid? Let's say two strings, right? So two words or two strings have small edit distance and then you merge them into a cluster. But what can be the centroid of the cluster? Here, obviously, we cannot average two strings and take the average, right? That's not defined. So what we have to do in this case is we have to choose one element from the cluster as a representative or similar to centroid. So in case of Euclidean distance, what happened was, yes, we choose a representative, but that may not actually be one of the real points. We actually take an average, and that centroid actually may not be one of the points. It just represents the general concept of the cluster. Here you have to choose one element from the cluster itself, which is an existing point in the cluster. And how do you choose a representative X in a cluster C? Okay, so we minimize. So one option is minimize the sum of the distances from X to every other element, similar to center, right? So similar to center, that means choose a choose an element which has the total sum of the distance to every other element is the minimum, or you minimize the maximum distance from X to any other element. So that means, okay, this is more like the radius. The previous one was more like the sum. This is more like the radius. That okay, it should not be far apart from any point at all in the cluster. And it could be another possibility is this analogous to center. Another possibility is minimize the sum of the square distances from X to any other element in C. Now this sounds similar to the first option. How is it different from the first option? Okay, so I'll leave this open as of now. In one case, you simply sum the distances from X to any other element in the cluster. Another case, you sum the square distances and you want that to be the minimum, right? So essentially, if there are some outliers and things like that in the cluster, some points are a bit far apart, then the square distances will blow up suddenly, right? So there will be some differences in that way. That's just a hint, but you can actually draw some figure and figure out what exactly happens. Okay, all right. So I think, yeah, it's like we are, so time is over. So yeah, so that's pretty much it. Any question at this point? Okay, so I will stop the recording.